hot topic, let's talk about software-oriented architecture. Our next presenter is Anil Dhonde. He's working for a very exciting startup called Ethernovia. He has impressive 28 years of experience in software, in particular in the semiconductor industry, on networking, switching, routing, and artificial intelligence. He held senior management positions, worked as a technical architect, and founding roles in a couple of tech startups. Anil studied computer science and received his master degree from Dalhousie University in Canada. Anil, floor is yours.
Thank you. First of all, thank you for the opportunity, especially in the presence of Bob here. I'm going to talk about futuristic automotive software architecture based upon microservices, orchestration, and networked hardware. I'll first go through some key concepts. Then we look at Ethernet as it exists today in the automotive world. Then we look at the futuristic software architecture, DevOps, which is development and ops, and the advantages to it. Then we'll look at pros and cons of this architecture as a whole. And then we will go into looking at the future work ahead of us. Traditional software that exists in cars today is built as a big monolith image, a single image on an ECU, for example, with software applications, operating systems, services, hardware drivers, and hardware. Typically one single image where applications are actually chained to hardware. They can't move outside. They have to reside on the same ECU, typically where hardware resides. This one single blob or image is quite difficult to manage, especially if you're making changes. Even a small change would need a rebuild, retest, integration, release, and update. So it's difficult to develop and difficult to deploy. If you look at the OEM software supply chain today, OEMs typically offload their software to tier ones who also tend to build ECUs in the supply chain. Every tier one would have their own platforms, software, hardware APIs, and hardware, which makes it which adds a lot of diversity in the platforms that you have. So the OEMs go into an integration phase when hardware and ECUs are available from the tier ones. And this integration phase takes 18 to 36 months of putting together different systems, testing them, integrating them, deploying them, going into an iterative cycle of changes, which is very painful for the OEMs. What the enterprise world, or the cloud world as we call it, the server market, has figured out to break down software into smaller pieces called microservices and applications. What is a microservice? A microservice is a small, dedicated piece of software that exposes a hardware function to an application. What is important to note here is that microservices and applications are very loosely coupled. There is no tight coupling. They do not have to reside on a single compute unit. They are talking to each other via a network. Microservices talk to hardware. Applications do not talk directly to hardware. They talk to hardware via microservices. What does that give you? That essentially gives you location freedom. Microservices can now reside in different ECUs compared to the applications. So what we are tearing down here is the design complexity of a monolith to smaller microservices. This gives you independent life cycle. A small change to a microservice, for example, only needs to change that microservice and update and release, compared to changing the entire monolithic image. Hence, build, release, update cycle is much easier when you break down the system, which is what the cloud world has been using for more than a decade. As soon as you get location freedom to microservices, what happens is these microservices can move around. They can sit on different compute units, which automatically brings you down to platform dependency. Operating systems, Linux, QNX, AutoSAR, RTOSes, services, network. Containers in the cloud world abstract this dependency of platforms to the microservices and applications. So then they can sit on any ECU without worrying about the services network underneath. Docker is one of the best examples of containers in the cloud world. What philosophy is followed here for containers is build your software once and run it anywhere. As soon as you have a multitude of containers in your system, typically in a cloud world, automatically somebody has to manage it. That choreography is done by an orchestrator. Kubernetes is one of the most popular orchestrator in the cloud world from Google that helps you manage these containers at runtime. You can configure the microservices and the applications. You can manage the life cycle, meaning updates of a microservice, for example, for a change. You don't have to update the entire system. You can do surgical updates. You can load balance, for example, a microservice that is catering to a hardware piece. If it gets bogged down, you can create a clone and take pressure off the microsystem. And if it's less loaded, you can do the reverse of it as well. You can create redundancy. You can create redundant paths, for example, safety or availability. You can isolate your faults much easier when you have a broken down system versus a monolith. You can fault identify, detect, recover fairly easily. And if you look at it at the end, all microservices in a system like this are routed through the orchestrator, for example, discovery and publishing your services. The OEMs have realized over these few years that software is the differentiator of the future. That is where their destiny lies. They want to build all or most of their software applications in-house compared to today where they are built at the tier ones. Some OEMs are already, as you know, are setting up their entities, and most will follow for purely software development. OEMs want full control over their software destiny, and that's where we are headed with this presentation, software. If you look at the state of Ethernet today, particularly in automotives, we hear most of us come from the Ethernet and specializing in the TSN background as well. 802.1 has given automotive Ethernet three things. It's now time-bound, it's deterministic, and it's reliable. These three ingredients help us imagine and deploy a software architecture that is based on Ethernet as a backbone. Let's see what the futuristic architecture looks like. So this is a simplistic view of the architecture and basic building blocks. At the center here, you see is in-vehicle cloud. Now note, don't mistaken this with the enterprise cloud like an AWS or a Google cloud, which is outside the vehicle. This is inside the vehicle, entirely inside the vehicle. It is networked to different components using, obviously, our favorite, Ethernet. On the far side here, you see an example of a hardware piece. Whether it has an Ethernet port natively on it, or whether it has a CAN bus or a LIN bus, a non-native Ethernet, it can be connected to an ECU with simple hardware APIs, like a driver. Again, bringing it into the network at the center, which is the in-vehicle cloud. The software pieces here, which we saw as key concepts, applications, microservices, containers that they sit in, the orchestration of these containers are run on different ECUs or compute resources. The beauty of this is there are no hard ties. The hardware piece, being on the network, is accessible from any software piece of this puzzle. Typically, applications will talk to hardware via microservices. For example, now, a software piece sitting at the head unit can access a hardware piece at the tail unit without having to worry about three things: platform, the hardware itself, and topology. This is completely topology independent. So you get full location freedom for your software primarily, and then hardware at the end. You can use Ethernet links, as shown here, as well as non-Ethernet links connected to ECUs to expose your hardware into the in-vehicle cloud. As soon as you give location freedom to software developers like me, then everything is only limited by your imagination. You have endless possibilities to put your software on different residences, different ECUs, different computes. Your microservices, your orchestrator, your containers don't have to run on single ECU, don't have to be tied to each other. Everything runs through the in-vehicle cloud. That's the beauty of Ethernet. What it did to the enterprise world in terms of cloud, we are bringing it right inside a vehicle. Here, it's important to note that any and every hardware piece, be it a CAN, be it a LIN, FlexRay, CSI2, whether it has an Ethernet port on the hardware, or whether it's exposed via an ECU, is all directly connected to the in-vehicle cloud and not to any ECU or any particular topology. So freedom, freedom, freedom is what you get out of this. At the crux of this architecture is networked hardware. Any piece of hardware that you have in the car, be it Ethernet or non-Ethernet, is exposed to the in-vehicle cloud. This is the most important piece of this. Without this piece, none of this freedom that we are talking about will exist. And software development essentially needs freedom. Once you get to networked hardware, what automatically happens is Ethernet ubiquity. Everything in the car is Ethernet. I'm sure Bob loves to hear this. Absolutely every piece of hardware or software now talks via Ethernet. Any piece of hardware that either has a port or is exposed via an ECU with an Ethernet port can talk to a switch at the edge, which in turn talks to a switch or more at the aggregation point, and that to the core. Again, topology independence is brought about by these Ethernet switches spread over the car. What we have done here in the last few slides is completely unshackle software stacks versus hardware stacks. On the left here are applications sitting in their containers, talking to microservices, not directly to hardware. Microservices, in turn, in their containers are orchestrated by the orchestrator, talking to hardware APIs over the network, for example, drivers or APIs. There is no hardware topology or platform dependence on the hardware, which is now brought into the cloud via switches at the edge, aggregation points, and the core. Let's see what are the advantages that this architecture brings to the development and operation side of the story, which is called DevOps in the software world. Traditionally, an OEM develops hardware and software in a serial manner. Hardware is first available, then software comes in picture. Hardware is a precursor to software implementation. This is a typical waterfall system. usually takes years before software can start their game. And then you get into software development, integration, then testing, then going back with your bugs and issues, then again iterating this cycle. Versus, where is the software world going? It's going into an agile system, wherein software and hardware should ideally move in parallel. In fact, I go ahead of this and say, software should come before hardware in terms of definition. Why? Software-defined vehicles, all of us are talking about it. But if we depend on hardware, then how can software come before it? So ideally, software should be hardware agnostic during development. You should decouple hardware and software development lifecycle and then ops lifecycle. If you can achieve this in an agile process, we will be able to pull forward our SOP by at least 2, if not more. 2 to 3 years is typical. But how do we achieve this? Let's see in the next few slides. Most of us in the software world have seen this diagram. It tells you that development and ops should be in complete cohesion. It's never a single cycle. It's always an iterative cycle. But if you're able to decouple your software and hardware development cycles, then this is possible. And this saves you a lot of time in the SOP, as we'll see shortly. This is for developers, particularly software developers. What you have at the center is our in-vehicle cloud that we saw. On the far right, what you see is digital twins. If you want to decouple your software development from hardware, models, digital twins, virtual hardware, C++, Simulink, MATLAB, all these technologies together can create hardware pieces as long as they talk the same interfaces, that is APIs, to the in-vehicle cloud. If you get to that point, then these software pieces that are being developed, designed, integrated, will not even know or should not even know whether it is physical hardware or whether it's virtual hardware. The beauty of this is Ethernet in between, or the cloud. The software has its own trajectory of development. Hardware pieces can either be legacy hardware that is already available in physical form, or digital virtual hardware assisting software development far ahead in the game. Now let's look at ops or operations. Operations, guys, are typically building, integrating, testing, releasing, updating through the development process and also beyond production. As the physical hardware pieces come along during the hardware development cycle, they replace, essentially plug in or plug out, the digital pieces on the right side. As you can see, the left side hasn't changed at all. The left side doesn't care and shouldn't care. Software should not care whether it's physical hardware or virtual hardware. To a certain degree, software should not even care the resources that are available in those hardware points. If we can create this software-hardware decoupling, complete disengagement, what you can envision is the in-vehicle cloud on the right side here can easily mix with today's enterprise cloud. What stops us from taking some of the microservices from the in-vehicle cloud, moving them into the enterprise cloud, and vice versa, which some people are calling it cloud native, mixed cloud, hybrid cloud, all those buzzwords. But in essence, if you create an in-vehicle cloud, any and every non-safety software process could go outside the vehicle with restrictions like safety, security, and resources. You can't have all the resources outside your vehicle. The edge, which is at the edge of your enterprise world to your in-vehicle world, now becomes a cross point for moving software pieces outside. And you can go even further saying that ECUs can now be moved into the cloud. Sounds funny, but you can take your software pieces and run them outside with restrictions that we talked about and use all the compute horsepower that is available outside. Let's look at the pros and cons. For development, you're completely breaking down the design complexity. Big piece of blob software compared to smaller manageable pieces in microservices, applications, containers, and then orchestration. Scalability. You can easily turn on, turn off microservices based on your vehicle models and scale it. Software does not have to change, only the scale has to change. Independence of platform, hardware, and topology. All three very important components to a software architect. All of this is going in an agile fashion, like the software dudes would like to do. It is no longer waterfall. You're shifting left. You're bringing in, you're pulling forward your SOP. You're doing a lot of early validation. If this concept really goes to its extreme, your software will be production ready or as close to production ready before hardware comes in picture. This is a very supplier friendly environment because tier ones can do their own do their job doing their hardware, software pieces. As long as everybody talks the same API over the in-vehicle cloud, you can integrate it fairly easily and not nightmarish integration as OEMs are used to now. Enhancements and future revenue streams are much easier. For example, upgrade a microservice, just a small update, not a big thing. If say in 2028, a robotaxi wants to release a new revenue stream feature with a new ad, it just turns on one microservice as an update. You don't have to go and upgrade the entire system over OTA. Extremely important for update cycles as they get shorter and shorter. Hybrid possibilities. You can move ECUs to the cloud, you can move software pieces to the cloud, you can use the power of compute resources outside the vehicle and extend your car's range. Advantages to the ops folks or the operations folks. The biggest one is time to market. If you can shave off 2 years in your car cycle, brilliant, people will love this. Load balancing. What if a microservice starts getting bogged down? You can create a clone, create a redundant path. You can reduce microservices based on your needs. So it's very orchestrated and manageable at that point. Failure detection. When you have an orchestrator sitting there as a choreographer, absolutely easy to get down, zero in, isolate your failure, and then recover your failure based on constraints. Life cycle updates, as we saw, the CI/CD pipelines, as the software dudes call it here, which is continuous integration, continuous development, is much easier when you are dealing with smaller pieces with their own life cycle, releases, versions, updates. Canary development. This goes back to the coal mines, where they used to send canaries, poor things, to detect if there is a fatal gas in there. Well, less graphic in the software world, as I would like to say. But you can do what they call in philosophy is fail small, fail fast. You can release your microservices and software pieces to a small subset of your cars. So if they start failing, you can backtrack very easily without destroying your entire world of cars. So that's canary development. Last but not the least is policing. With an orchestrator, the beauty of it is visibility in what's going on inside a car. Monitoring, which ends up letting you police not just one, but an entire set of cars that you can do. Obviously, there are challenges. It's not challenge-free. The first challenge that we see is it's a cultural shift. It's a mindset. Most software and hardware designers are used to having hardware, then software, then a monolithic image, all put together in one package. It's a steep learning curve to break designs. But once they learn how to break designs down into smaller pieces, then it becomes very easy, and I'm sure they will not go backwards. Validation, we saw endless possibilities, but we are in automotive. We can't really rule the game with endless possibilities. So you have to come down to a manageable subset of possibilities that can be validated, tested. Overheads. There's certainly some amount of overhead to the software pieces, particularly around containers, services, and different pieces that we are building now, including the orchestrator. So there's memory, footprint, and processing constraints. Legacy hardware. For example, an ECU that does not even have a 10 megabit Ethernet port. How do you integrate it into the system? So that's a challenge. So we'll eventually have to come out with a solution which integrates legacy pieces via some form of Ethernet, because Ethernet is the base of all of this. Compatibility. A tier one, an OEM, they have to all agree with compatible APIs, interfaces, strict standardization, which is difficult to do. To summarize, what we saw was monolithic software is painful to develop and deploy. Ethernet allows you to break down this monolith. Futuristic architecture here that we are proposing gives you endless possibilities, only limited by your imagination and resources. Ethernet ubiquity across the car. As soon as you have Ethernet over the car, essentially networked hardware, you can achieve all of this fairly easily. The benefits of this architecture to DevOps, and then the mix of enterprise cloud with the hybrid cloud. As they say in the Silicon Valley, it takes a village to raise a kid. So obviously this is not something that one company, one group, or one team can do it. It's way beyond the resources that one entity would have. Let's look at the potential future work items that we see. One is creating lightweight pieces of software. Containers, orchestrators, they have to be light enough to go in a car so that they don't take more power and give you less range. Networked hardware and standardization of APIs is important. Network. That is the key to this. And APIs for hardware to talk to software pieces is important. There's a lot of work involved in this. Safety, reliability, and security are a different ballgame now. You have to have a very modern approach to what this architecture will need and compared to what you have today. Concluding thoughts, software and hardware. Software, think cloud first. Everything you build should be built with cloud first. Whether it's a small piece or a big piece, think in-vehicle cloud first. If that is achieved, you can move it around. Hardware, very obvious. Ethernet, network. Ethernet ubiquity is what we should natively think when we build any piece of hardware. Thank you very much for listening. I'm open to questions.
Thank you so much. So I do have a question. You mentioned API standardization. Where? Which organizations are you addressing?
So today we are opening up this as an architecture. It's not like it has been years of development, but we are looking at several efforts out there. SOFI being one of them, that's we're looking for contribution. We're looking at other forums as well, but it's not an active participation, it's just an exploration right now.
Mm-hmm. Okay.
Thank you for the presentation. So Oliver Crichton from BMW. In principle, I couldn't agree more with what you discussed. I wish you could make more actionable the parting thoughts you gave to us, because I do think cloud first, but it's clouds. And there is an important distinction to building billions of clouds for this world and just having one or a couple of clouds like we see in the IT world right now. So I would say and argue that this is, of course, the right vision, but the question is really how do we get there? And with getting there is, thank you for acknowledging that it's a painful and nightmarish process to integrate at the OEM level. We don't do this because we want to.
Yeah.
We do this because we have a responsibility for the safety, for the security, for the reliability. And so if you are abstracting away most of the things by having a clouds first, billions of clouds that you're building, the question really becomes, how do you do that you are still able to make the safety cases? How do you define these safety elements out of context? How do you ensure security for every single vehicle? Because I sure don't want to sit in a canary vehicle.
Very nicely said. Thank you, Oliver. You raised a couple of very good points. Obviously, I don't have answers to everything here. We're just putting this together over the last year and a half or so. Actionable items, certainly we are thinking of focusing on smaller areas of this over the sequential presentations that we plan to do, and obviously this committee accepts us talking over them. There are some discussions in the background. To be very honest, this was the first presentation of this sort that we wanted to do. So we wanted to keep it at a higher level so that we get the message across and people like yourself start talking about it. That's the crux of it. As we get and dive into compartments of this architecture, we will do more presentations, bring it up to forums, and we would love contribution. We would be part of the puzzle, and we would love absolutely OEMs, tier ones, vendors, technology companies, looking at this from different perspectives and contributing. Did I answer your question? Yeah, thank you.
Thank you. Next question.
Thanks for the presentation. I'm Rajiv Roy from NXP, a bit reflecting what Oliver said.
Yeah.
And to carry on with the aircraft analogy, I guess the most obvious, there was Airbus and then there was the 737 MAX.
Yep.
The problem with decoupling software with hardware, the big thing is the disconnect. One essential point of element that you bring in is the digital twin.
Yep.
It's almost impossible to replicate the real system.
Yep.
So if you are bounding the use cases, you need to know what the system is, and you don't have that. So you need to have a slight bit of lockstep between the software and the hardware cycles. Mm-hmm. And that's a bit of concern I would have with this kind of model. Again, I wouldn't want to be in the Canary Island. And again, the small feature which was introduced in the 737, sorry, a small failure led to 2 planes crashing. And a lot of people did not make it. And that kind of thing is something which would concern me a lot. So I'm not sure it's a question, but to me this seems a bit utopian. Thanks.
Yeah. No, Rajiv, thank you for the comment. I have expected this. I have heard this as well. Yes, but my colleague here, Brian Peterson, on Sunday said a wonderful thing when we were talking about something like this, is that if we don't dream, then we better not be here. So yes, this is something out of even our comfort when we started looking at this. Coming back to your point about hardware and constraints and obviously testing validation, that is an important piece. I'm not saying here or not even claiming here remotely that the digital piece is your final game for validation before you deploy it. Now there will certainly be an integration, testing, validation, FUSA, safety, security, all of those measures. But what we are trying to do is take some of that load off during development. Right now, if you wait for all of this to be available in physical form, then you waste 3 years or more. I'm sure the colleague at BMW would agree to that. So we are taking that cycle off. Finally, you're testing for 6 months or 8 months. That has to be done. There is no other solution to that.
I completely agree to that. I think software development can start way ahead.
Yes.
But I know it's a high-level presentation.
Yeah.
But maybe in the graphs that you show, where you cut down 2 years from the SOP, you need to have a slight bit of offset where there is still a testing done on the real hardware.
Yes, we will. We do plan. In fact, we are working on successive presentations to this, focusing on areas. But I like to keep it at a higher level here, essentially to what you're saying. Start raising the dialogue, the comments, and the critique is very important as well. Obviously, we don't have everything figured out here. Over the next 4 to 6 sessions, I'm sure there'll be focused presentations, if assuming the committee likes me to talk about it. And all of you are welcome here to work with us, partners here, to help develop a vision like this. Yeah.
Thank you.
Thank you.
I think you need to consider to have a forum where you can discuss. It's very crucial.
Yes, working on it. And if anybody has suggestions here, please bring them on.
Okay. Anything else? No? Then we'll break for a coffee break and we'll be back at 11. Thank you.
Thank you.